Bismillahirrahmanirrahim. Class, today our topic is about a bridge. It's introduction to bridge engineering, and I will try to explain different components of bridge, and then move on to the design, including the analysis. So let's go to the contents. These are the topics that we will cover, starting from introduction, bridge components, types of bridges, loads for bridge design, analysis and design of simply supported RC slab bridges, and following an example, solved example, and then some famous bridges in the world. Okay. The objectives are at the end of this lecture, you will be able to differentiate between bridge and culvert. You will be able to explain how different type of bridges resist loads, and you will be able to analyze and design a simply supported RC slab bridges. Okay. Now coming to the introduction, bridge is a structure having an opening not less than 6,000 millimeter. Okay, it's a 6,000 millimeter, which is equivalent to 6 meter, that forms part of a highway or over or under which the highway passes. Okay, so it is a part of highway, over a highway, or under the highway. Structures less than 6,000 millimeters span generally called culverts. So you are understanding the difference between bridge and culvert. Culvert is uh, less than or equal to 6 meter, and bridge is more than or equal to 6 meter. It's all about the span length. Okay. Bridge is the key element in a transportation system. It controls the capacity of the system. It is the highest cost per mile of the system. If the bridge fails, the system fails. Okay, so for example, you have a road. Let me show you explain you the figure. For example, the road is coming from this side and continuing on this side. This is the bridge. Now the per unit cost of road over here and per unit cost of road over here will be much more lesser than the per unit cost of road or in this span length, because of the construction of the bridge. Okay, so it is the highest cost per mile of the system. It controls the capacity of the system. For example, if the road width is 4 lanes over here and 4 lanes over here, and you have constructed a 2 lane bridge, so the purpose will be failed, because the traffic coming from this side, the 2 lanes will be submerged into 1 lane, and they have to wait over here. Similarly, the case, the traffic coming from this side have to wait over there. So if the bridge is of not the equal span of sorry, the equal number of lanes to that of the adjoining roads, then it is of no use. So the bridge controls the capacity of the system. It is the highest cost per mile, and if it fails, the system fails, because if the bridge fails, the road will be of no use. So the 20 kilometer or 100 kilometer road will be of no function if this small portion fails. So this is the key element that need to be designed and analyzed carefully. These are some of the basic components of a bridge. A bridge consists of superstructure and substructure. And what are superstructure and substructures? You can see that superstructure are the structural parts of the bridge which provides the horizontal span. Okay. Substructure are the structural parts of the bridge which supports the horizontal span. So over here, this is your superstructure, right? And beneath these are the substructures. This is the horizontal span. This is called the superstructure. Okay. And the components that are supporting this superstructure, the piles, the pile cap, the piers, the bearings, everything, these are substructure. Okay, the abutments are substructure, and this deck and girders, these are the superstructure. So this is the main difference between substructure and superstructure components. Now continuing those components, so you can see that these are the piles, the lowest part of the bridge piles, right? Right here you can see the piles. On the piles, above the piles, there is a pile cap. The pile cap is supporting the pier. The pier is then converted into pier cap, the cap of piers. Okay, and the pier cap is supporting the girders. These are the girders. the girders are supporting the deck slab. Okay, so this is the mechanism. You can see the transom as well, you can see the diaphragms as well. So these are the different components of a bridge, of a typical girder bridge, not the slab bridge, not the cable stayed bridge, not the suspension bridge or other types of bridge. This is a simple girder bridge. So coming to the point, how many types of bridges are there? Bridges can be classified according to materials. For example, made of concrete or steel or wood, etc. Usage, what kind of usage it has. For example, the pedestrian usage or the highway traffic or a railroad traffic. What are the spans? For example, short span bridge, the medium span bridge, the long span bridge. Usually, short span are girder bridges, medium are cable stayed, and long span bridges are suspension bridges. Structural form, for example, slab bridges, girder bridges, truss bridges, arch bridges, suspension or cable stayed bridges. Okay. So it is, however, suitable to classify bridges according to the location of the main structural elements relative to the surface on which the user travels. So there is another classification of the bridges according to what? The location. For example, if the main structure is below the deck line, or if the main structure is above the deck line, or if the main structure is coinciding with the deck line. So there are three types of bridges on the basis of location of main structural elements, and I will explain in the coming slides. Okay. Now coming to the first type, when main structure is below the deck line. So you can see the example of arch bridges. See, masonry arch bridge and steel deck truss bridge. In all these type of bridges, you can see the deck line where the people or the cars or traffic travels. So the main structure is below the deck line. Deck line is over here, and all the main structure is below this line. So all truss arch bridges, masonry arch bridges, concrete arch, steel arch, and the steel deck truss bridges are in this category where main structure lies below the deck line. The second one is when main structural, I'm sorry, this is the continuation of the previous slide where different types of bridges are shown, where main structure is lying below the deck line. So you can see over here as well that all these bridges, the deck line lies above the main structure, right? Now, discussing the mechanics of main structure below deckline. With arch shape, gravity loads are transmitted to the supports primarily by axial compressive force. At the supports, both vertical and horizontal reactions must be resisted. So this is what you have learned in structural analysis, right? The analysis of arches. So there is a horizontal thrust and there is an axial force. So arch must be designed for that. Uh, and both horizontal and vertical reactions must be resisted at the support. So in this case the support must be stiff and strong enough horizontally as well as vertically. Some key features of this type of bridge are that the arch form is intended to reduce bending moments in the superstructure. The most suitable site for this form of structure is a valley with the arch foundation located on dry rock slopes because the foundation must resist the horizontal and vertical reactions. So, a dry rock will be a suitable position. The conventional curved arch rib may have high fabrication and erection costs, although these may be controlled by skilled laborers. The classic arch form tends to favor concrete as a construction material. So these are some salient features of this type of bridge. The other type is when main structure lies above the deck line. So the suspension, cable stayed, and through truss bridges are the main examples. You can see uh, the deck line and you can see the main structure. Okay, the main cables, the hangers, and the towers. All the main structure is lying above the deck line. This is also a suspension bridge. Similarly, cable stayed bridges. Let me show you that. Yeah, see the cable straight bridges. This is the deck line, and these are the cables, and these are the towers. So main structure lies above the deck line, right? Over here as well. And and the through truss bridges, where you can see this is the main deck line, and the trusses, all the trusses lies above the deck line. So these are the examples of main structure above the deck line, right? The important features of this kind of or type of bridge is the flexible cables of a suspension bridge are shaped and supported to transfer major loads to the towers and anchorages by direct tension. So in suspension bridges, the deck load is transferred to the cable via hangers, and the load from the cable is transferred to the uh, anchorages and the towers by direct tension in the cable. The deck is hung from the cable by hangers constructed of high strength wire ropes in tension, as I explained. This use of high strength steel in tension leads to an economical structure, and these are used for the long span structures, right? For example, the Akashi Bridge in Japan, it is a suspension bridge. Some more features: the main cable is stiffened either by a pair of stiffening trusses or by a system of girders at deck level, right? This is all we are talking about suspension bridges, one of a type of main structure above deck line. This stiffening system serves to control aerodynamic movement, the movement of high speed wind, and limit local angle changes in the deck, right? The stiffness or the serviceability of the deck remain intact during the wind storms or something like that, or even the passage of the traffic. So you can see how they maintain the stiffness of the structure. Some important features of the cable straight bridges is, as compared to suspension bridges, the cables are straight rather than curved. Okay, in suspension bridges, the main cable is curved. However, here the cables are straight. As a result, the stiffness is greater. Aerodynamics instability has not been found to be a problem in this kind of structure, as we discussed in the suspension bridges. Okay, and the through bridges, a bridge truss has two main structural advantages. Number one, the primary member forces are axial loads, and number two, the open web system permits the use of a greater overall depth due to lesser dead load than for an equivalent solid web girder. Both these factors lead to economy in material and a reduced dead weight. The increased depth also leads to reduction deflection, economical for medium spans. Keep in mind that this is not for a long span structures, okay? And aesthetically pleasing. These are the some important features of through bridges. The third one is when main structure coinciding with the deck line. Girder bridges of all types are included in this category. So first one was arch bridges, second one was suspension and through bridges and cable straight, and third one is all the girder bridges, right? Where examples are slab, T-beam, I-beam, wide flange beam, concrete box girder, steel box, steel plate girder, all lies in this category of main structure coinciding with the deck line, right? So you can see very clearly that the main structure, which are girders and the deck slab, in this case lies at the same level. Box girder bridge under construction, where you can see that the I girder or steel girders are used by the manufacturer, and the deck slab they lies at the same level. So these are different examples. For example, the T-beam bridges, the pre-stressed girder bridges, the slab bridge, you can see no beam or girder here, and the box girder bridges. Okay. Now, having discussion about the types of bridges, we are coming to the main topic. The loads to be considered in bridge design can be divided into two broad categories: permanent loads and transient loads, and both are equally important. Okay. Now, taking the first category, permanent loads. Self weight of girders and deck, wearing surface, curbs and parapets and railings, utilities and luminaries, and pressures from earth retainments. These are all permanent loads and will stay there as a dead load throughout the lifespan of the bridge. Two important dead loads are DC, which is called dead load of structural components, and non structural components. and dw, which is dead load of wearing surface. Why we are taking it very as different? Because the wearing surface may differ at different phases of design life of the structure. Okay, so in the permanent loads, the material properties for pavement, we take bitumen unit weight at 140 pound per cubic feet and concrete unit weight as 150 pound per cubic feet. And load factors, we take 1.25 for the concrete or the structural and non-structural components, and 1.5 for the wearing course weight.